Hi, welcome back to a video series on MAT 1033 Intermediate Algebra. My name's Sean Perry. This is video number 12 in the series, Slopes of Lines. So I think a very important concept in mathematics is that when you're introduced to some new piece of information or some new nomenclature or some new object, you shouldn't immediately think that it's going to be something completely alien. You should, in fact, try, if you can, to tie it to something you're already familiar with. And the idea of slope is one that you've already been exposed to. You've been thinking about it since even before you knew what a number was. Now, that's because I'm pretty sure you've been walking since before you've been counting. And if you didn't know how to estimate how steep the ground was, whether it was rising or falling under your feet, you'd fall right down. So we should try, when we learn new things about this concept that we already know, to tie it back to the physical thing that we're already familiar with. You already have an intuitive sense of rising and falling. So whenever you learn these new concepts, try to ground them back in that physical understanding that you already have some experience with. Let's start with the idea of what it means to be steep. If you were to climb a steep hill, if you went forward a little bit, you would go up by quite a lot. And so what we want to think about is that as we run in a horizontal direction, and I just want to get you used to this idea of run to the right, we're always going to be considering movement from left to right. How does that correspond with our up and down movement? If we go up a lot when we go to the right a bit, then we're going to have a large positive slope. It's large because it's steep, and it's positive because we're going up. And likewise, if we run to the right and we only go up a little bit, then this is going to correspond to having a shallow slope, a small positive slope. If it goes up a little, when we go over a bit, then that's going to be a small positive slope. And keep in mind, we're always going to run, that's right, to the right. Now, what about if it goes down? Well, if we run to the right and it falls somewhat, goes down a little, this is a small slope, a shallow slope, but it's also a negative slope, meaning we're going down. And unfortunately for our friend here, if we go to the right and we fall down a whole lot, that's going to be a very steep and also negative slope. We think of this as declining in a big way. So movement to the right, followed by a big downward movement, is a large negative slope. But what about if we don't go up or down at all? What about if the ground is flat? Well, we're going to call that zero slope. No, not no slope, but zero slope. The slope measurement, how much we went up or down as we went to the right, we went up or down by 0 feet. And what about for vertical lines? What about if there's no run to be had? We're not going to the right at all. It's just going, well, up or down, depending on your perspective. For this poor fellow, he's going down quite fast. He's just falling. That's going to be called an undefined slope. And we'll see why in a little bit when we look at the formulas for slope. But for right now, I just want you to think, if I'm not going to the right or left at all, then I can't really calculate how much I go up or down when I go to the right by a little bit. There's no right to be had. I'm not going right. You could also think of this as being infinitely steep, but I really encourage you to adhere to the idea of saying that this is an undefined slope when you see a vertical line. So at this point, I want you to copy this holistic understanding of slope into your critical notes. Draw all 6 of these pictures and label them accordingly. Which one has a little positive slope? Which one has a little negative slope? Big positive, big negative, and 0 slope and undefined slope. You should copy all these down at this time. So, of course, we can't just leave things with words. This is math, after all. So let's get some numbers and symbols involved. I want you to consider the following graph. So here I've drawn a blue line right here. And I want you to notice I've drawn some triangles accessory to that line by making vertical and horizontal lines that meet each other, but have this blue line as their diagonal. Now I want you to notice that all these triangles have a pretty similar appearance, don't they? In some sense, they're not different triangles, they're similar. They have the same ratio of sides. They're just of different sizes. But something that you should remember about similar triangles is that the ratio of their legs is always the same. You know, this black delta x and this red delta x, we'll talk more about that symbol in a second, They might be different in size from one another, but if we compare them between each other, black to black, red to red, or yellow to yellow, they're all going to have the same ratio. And it's that ratio of upness to overness that's going to be used to define slope. So just to be very specific, this ratio, how much they went up or down versus how much they went to the right. Those are all equal. Now this delta symbol is an uppercase Greek D, and it's actually quite old. It's been in use since before science was science. It once signified the element fire, back when we used to think of elements in a more primitive sense. And we use it still because of the association with fire and change. Even air sits still sometimes, but fire never stops moving. And so the ancients considered it to be the element of change. We now still use it to mean change in some quantity. So the expression delta x, which you could read as delta x or the change in x, means how much did the variable x change in value? And so we could think about slope in terms of this change. Slope can be thought of as the ratio comparing how much the variable y changes to how much the variable x changes. So with that in mind, here's some more critical notes. Copy this picture down. This distance here, which is the change in x going from this point to this point along the line, and this distance here, delta y, which is the change in y as we go from this point to this point along the line, are going to get the names delta y and delta x. And our slope is the ratio of delta y divided by delta x. Now I want you to think about how that relates to our holistic understanding of slope. If delta y is small, then this number will be small for given values of delta x. Let's consider delta x to be 1, for example. If delta y was small, then this would be small. If delta y was big, this would be a very steep line, and this would be big. And it also makes sense with what we learned about positives and negatives. Then if we were going down in some sense, then this delta y would be negative. So in that regard, it's not really a distance, it's a displacement, but let's not put too fine a point on it. Instead, let's do an example. What's the slope of this line? Now, I didn't tell you anything about it other than from here to here, it goes over by 7 and down by 3.5. The negative sign means that it's going down when we are traveling from left to right. So what's our slope? Our slope is going to be the change in y, negative 3.5, divided by the change in x, which is 7. Now you could type that into your calculator, or you might actually know how to do 7 into 35. This is negative 0.5. Negative divided by a positive is a negative, and 3.5 divided by 7 is 0.5. We could also write that as 1 over 2, negative 1 over 2. Multiply the top and bottom by 2, and you'll get 7 over 14, and reduce to 1/2. So either one of these, they both have the same numerical value, just different forms, is the slope of this line. And notice it's a reasonably small number, it's negative, and this is a reasonably shallow line, and it's going down. So now let's talk about slope given 2 points, instead of just the change in those points. How do we calculate change? Well, let's think about this in a just one variable sense. If I start out at an x value, say 4, and I go to an x value, say 10, how much did I change? Now, don't be too put off by the 1 and the 2 here. What we're saying is they're related to each other. These are both x's, but this is at maybe time 1 and this is at time 2. We often use subscripts in mathematics to indicate that we're still talking about the same variable, but maybe with different values at different times or something like that. Here I mean we started at this value, 4, and we went to this value, 10. How much did it change? So we could calculate this by taking their difference. x2 minus x1 would be 10 minus 4, that's 6. And that makes sense if you think about a number line. If you go from 4 to 10, you've gone up by 6 units. Likewise, if we started at x1 equals 4, and then we went to x2 equals 2, we've actually gone down by 2 units. But how could we see that in our difference? Well, if I keep the order the same and I say x2 minus x1, then I get 2 minus 4, which is minus 2. And going down is related to this negative sign. Right? So keep that in mind. When we talk about change, the negative sign indicates that we've gone down. And then what we can do is then define what is the change in x. What does delta x really mean in terms of 2 points, x1 and x2? And that's going to be x2 minus x1. You really do want to put this 2 first and then subtract the 1 from it so that your positives mean increasing and your negatives mean decreasing. If you flip them, you'll get the opposite interpretation. And so using this notation, we can get a formula for a slope if we've been given 2 points, or if we can figure those 2 points out from a graph or something like that. And that's important enough to be critical notes. So I want you to copy this picture down. You don't have to color code it. It's just there to try to help. If I know 2 points on a graph, x1, y1, and x2, y2, then I can figure out the slope of this line by first calculating delta x and delta y. Oops, typo. This should be a y up top and an x on the bottom. Be careful about that. It's a common mistake. You just watched me make it. Don't you make it too. There should be a y up top. We're talking about change in y up top, change in x on the bottom. And what is our change in y? It's y2 minus y1. So we want to go and get the y values and take their difference. Over x2 minus x1. We get those values and take their difference. We divide those two differences, one into the other, and that number is our slope. So let's do another example. Let's say we have the line y equals 3x minus 1. Now it passes through the points 1, 2. You can get that by plugging in 1 in for x. 3 minus 1 is 2. And then negative 1, negative 4. Negative 1 times 3 is negative 3, minus another 1 brings us down to negative 4. So the line is satisfied by these two xy pairs. What's its slope? Well, first let's take those two pairs and label them, x1, y1, and x2, y2. If we then follow through the formula, y2 minus y1 over x2 minus x1, we get negative 4 minus 2 over negative 1 minus 1. That's negative 6 over negative 2, which is 3. 3? Yes, that 3. That 3 indeed. We'll come back to that. But one thing I want you to notice is that it didn't really matter which one we labeled x1, y1 and which one we labeled x2, y2. You might think that would matter, but it doesn't. Here's why. If I take y2 minus y1 and x2 minus x1, and I flip them both, not just one, mind you, but both of them. Well, flipping a subtraction, we saw, pulls out a negative sign, but a negative over a negative cancels. And actually, this expression is equal to y1 minus y2 over x1 minus x2. So even though it mattered what order we subtracted them in for individual x's or y's, when we look at the pairs of points, it actually doesn't matter. Isn't that curious? Now they still have to match up vertically. Notice the colors are still matching vertically. And I've made the colors match the subscripts so that you know which point they came from. Now, another thing that we might be able to do to simplify some of our work and take a little shortcut here is if we write the equation of a line involving x's and y's, and we simplify it after solving for y, we usually get the following. Y equals some number times x plus some number. Now, maybe these are ones and zeros, but as long as it's not a vertical line, we'll be able to get this into this form, where m and b are just numbers. We would say that x and y are variables and m and b are parameters because they're going to be fixed for the whole problem. But again, let's not get too into the weeds. M and b are numbers. In this case, that number m is the slope. Is that always true? Well, we've actually seen enough already with the formulas that we have to prove that that's always true. I won't show you too many proofs in this class, but I thought this one might be nice. Let's consider a line y equals mx plus b, and let's take 2 points on that line and call them x1, y1, and x2, y2. Now, if I plug those in, it should satisfy the line. In other words, plugging in x2 and doing m times m plus b to it, I better get y2. That's what it means to be a point on the line, is to satisfy this equation. And likewise for x1, y1. You plug in x1, then you get y1 back. Now here comes the cool trick. Subtract equation b from equation a. In other words, take what's on the left, y1, minus that from y2, and take what's on the right, mx1 plus b, and minus that from mx2 plus b. We're allowed to do that because these things are equal, and so by subtracting each one from each side, we really are doing the same thing on both sides. And here's what you get. You get y2 minus y1 from this difference, and you get mx1 plus b minus mx2 plus b on this side. Distribute your negative sign and regroup, and you'll get mx1 minus mx2 plus b minus b. Plus b minus b, well, that's just 0, so we might as well get rid of that, and factor out our m. Now, dividing by what's next to m, look what we get. Isn't that nice? We get the equation for slope. So yes, that number m is always your slope. So copy these last critical notes for this video. If you have a line of the form y equals mx plus b, which includes if m or b are 0, I will have you know, then your slope is m, the number m. We'll talk more of that later when we talk about equations for lines. But for right now, you should know this m, if we solve for y and we collect terms and we get y equals mx plus b, that m is slope. All right, let's take a look at some practical exercises for the day. I want you to think about these lines. The ones with arrows are lines. The ones without are just the coordinate axes. And I want you to tell me the slope in each case. Pause the video at this time. Okay, let's see how you did. Now, these first two are simple. All horizontal lines have slope of 0. All vertical lines have undefined slope. I want you to notice I didn't even put an equal sign here. It's not equal to undefined. Equal implies that it has some number value. What we're saying is it doesn't. It doesn't have a number value. And actually, I would be a little bit remiss if we didn't think about that for a moment. Before we go on to these other ones, I really wanted to say, what if I had 2 points on this line? x1, y1, and x2, y2. Well, for all points on this vertical line, they all have the same value for x. Let's call it c. And then my slope would be equal to y2 minus y1 over c minus c. Okay, well, wait a minute. That's 0. And we talked a little bit in the other videos, 0, you cannot divide by 0 because 0 has no reciprocal, right? You cannot divide by 0. Just in case we didn't mention that in a previous video, why would that be? Because if if you can divide by 0, you could divide 1 by 0 and get its reciprocal, which would be the number you multiply by 0 to get 1. But anything times 0 is 0. That means 1 is equal to 0? Of course it isn't. No, it's not. That's a contradiction. And because that's a contradiction, you cannot divide by 0. End of story. No ifs, ands, or buts. No matter what. And so in this case, with our definition for m, we cannot divide by m. Likewise, up here, we could have done the same kind of analysis for the 0 slope situation. And so let me just remark on that. Right? If we have 2 points on a horizontal line, our x values might be different. And so we would take and divide x2 minus x1 on the bottom of some slope. And on the top, well, they're both going to, the y1 and the x1 are going to, or the y1 and the y2 are going to have the same value. Let's call that d, right? And so we're just going to wind up with d minus d up top. That's just 0. And 0 over a number isn't a problem. 0 over any non-zero number is 0. And that's exactly what we asked you to memorize in the holistic version of this, that horizontal lines have slope 0. So just to remark, it does accord with our formula. Let's go through these a little bit more quickly. This is my delta x. This is my delta y. And so m, which is delta y over delta x, is just 2/3. Likewise with this one, we need to remark what is a x1. Doesn't matter which one I pick as long as I keep them together. Let's call this x2. And so our slope is going to be y2 minus y1 over x2 minus x1. So up top, I have y2, which is 0, minus y1, which is 2. And then I have 1 for my x2, minus 0. 1 minus 0 is just 1. 0 minus 2 is negative 2. And so we have a slope of negative 2. And yes, this line is declining. It's a little steep, so we shouldn't be surprised that it's a minus number greater than 1 here. Lastly, we just have to recognize here that this is solved for y. Then this is our m. M is equal to minus 6. Okay, that concludes this video. Thank you for your patience, and good luck with your studies. I'll see you in the next one.